So we'll be discussing fundamental theorem of arithmetic in the scope of real numbers. All right. Fundamental theorem of arithmetic. It's very basic. Basic as in it's very fundamental. You cannot skip it. All right. It's also called as prime factorization theorem. So you can probably guess that there is a lot of prime factorization that you would need to do. All right. We will not be discussing prime factorization itself, but basically how you can actually apply the prime factorization for various other interesting things in mathematics. First statement is from NCERT, which states that every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Right? There is a lot to process, so we'll break it down step by step. First up, every composite number. So in general, when you have a fundamental theorem or any kind of thing, it may be general. So it says for everything, all right? Every composite number. Let's take a composite number, maybe 12, all right? Let's just write down the prime factorization of 12. It will be 2 times 2 times 3, right? 2 times 2 times 3, right? So this theorem says that the factorization is unique, which means you can only write 12 as 2 times 2 times 3. And that if you take 2 2's and 1 3, you can only ever get 12. You cannot get any other number, right? Which is common sense. If you say if you multiply 2 times 2 times 3, you're only going to get 12. You can't get like 7 or 5, right? If you multiply 2 times 3 times 2 or 3 times 2 times 2, you're still going to get 12, which is the last part, which says that the order is not important, all right? Apart from the order. So that is what the fundamental theorem of arithmetic means. All it says is that, okay, you have a prime number, sorry, you have a composite number. You can break them down as a product of primes, and whatever combination you get, it will be unique for that given number. All right. Second statement is from Wikipedia. Now this one is slightly more formal, so we'll try to make sense of it. But even if you don't get this, don't fret about it. That's okay. It is true for every positive integer. The first difference, all right, the NCERT one only talks about composite numbers, but here you're talking about every positive integer, right? It says that there's exactly one way you can write any positive integer more than one as a product of prime powers, right? And this is the representation, continuous product. The pi is continuous product of the given prime numbers raised to appropriate powers, right? And they have said that you should arrange the prime numbers in ascending order. So for example, if we take the same example of 12, it says that you can write 12 as 2 raised to the power 2 times 3 raised to the power 1, right? So your two prime numbers, P1 is 2, P2 is 3, N1 is 2, and 2 is 1. And that is the only way you can actually get it out. There is no other way, all right? Let's see some problems on this. First problem, you have been given m unique prime numbers and a maximum of k each. How many numbers can you generate, right? Why are we even talking about this? Like, what would this help us achieve? Well, it kind of, tells you that, if you have got a given set of ingredients, what all dishes can you make with this, right? If you're given a set of elements, which compounds can you create from it, right? Like if you're given hydrogen and nitrogen, you can probably create ammonia, but you cannot create carbon dioxide, right? Because carbon dioxide requires carbon and oxygen. Similarly, if you're given some prime numbers, let's say 3 and 5, which numbers can come out of this, right? You can do 3 times 5, 15. Or you can do 3 square times 5, which is 9 times 5, 45. 3 times 5 square, 75. So there's only a specific category of numbers which will arise from the given base prime numbers, right? Now this question is relating to that aspect. It says that, okay, choose m unique primes, whichever ones you want. And you can have a maximum, multiplicity for any given prime number of k. That means, any given prime number can appear a maximum of k number of times, right? Now the question is, how many numbers can you generate? Let's take an example. Let's say m is 2. All right, so m is 2. Let's take the example as maybe 3 and 7. All right, so these are our two prime numbers. We can generate some numbers right away, right? Maybe 3 into 7 is 21, right? 3 square times 7, that's like 63. Or we can do 3 times 7 square, that is 147. So these are some of the numbers that you can get if you just multiply various powers of 3 and 7, right? But you cannot get 10, right? Because you don't have a 2 or a 5. So that's not possible. Let's take k as 2 maybe, right? So that means any multiplicity can be 0, 1 or 2. That's it. Only 3 options, right? So if you had two, if the value of k was 2, how many options did you have? You had k plus 1 options. That is the thing to understand, right? Because 0 is also there. So you can either have 0 of that prime number, 1, 2, 3, 4, 5, all the way till k. So what are the possible numbers here? Well, you can have, let's say we fix 3 squared. So we're going to take two threes. You can keep varying the number of sevens. 0 sevens, sorry, first let's start with 2 sevens, 1 7, and then 0 7. And then we'll do the same thing for 3 power 1. So 3 power 1 times 7 square. It's an, you can say it's a logical way of thinking about numbers. It's basically an arrangement pattern that we are seeing here, right? So 3 power 1 times 7 square, 3 power 1 times 7 power 1, and 3 power 1 times 7 power 0. And at the end, we do the whole thing for 3 power 0. So essentially, you're going to have 9 numbers. That is the theorem. Now, the thing is, if we generalize this, because we expect to give an answer in terms of k and m and not specific numbers, right? So you've got m boxes. Each box represents a prime number. Cool. Like we had 2 in the previous case. And within each box, you can put some certain number of balls, right? Which will be the multiplicity, right? So let's just take that maybe, let's just take the m prime number. So you've got like m boxes. And within each box, you can put any number of balls between 0 and k, both inclusive, right? So that means if you pick any one particular box, how many options are there? Well, it has got k plus 1 options, right? Because you can put 0 ball or 1 ball, 2 ball, 3 ball, all the way till k balls. And each of those m boxes have those options independently, right? So that is the fundamental theorem of counting, which is something that you deal a lot with in permutations and combinations, right? But it is a logical way to think about it. Like, just think about it. How many two-digit numbers will exist? Well, if you want a two-digit number, it's like having two boxes. The first box can have 9 options because you cannot have 0. So there are 9 ways to fill the first box, and then there are 10 ways to fill the second box, because you can literally put any digit in the second box. In the first box, you cannot put 0, otherwise that becomes a one-digit number, right? So 9 times 10, you will have 90 two-digit numbers, right? You can actually count. There are only 92 digit numbers, right? I leave that to you to basically convince yourself, right? So if you consider this over here, you have got m choices, and each of the choice has got k plus 1 options. So essentially what you have got is k plus 1 times k plus 1 times k plus 1, this continuous product m number of times. So overall, what do you get? K plus 1 raised to the power m. As an extension to this, we can think about how many of the generated numbers will be prime numbers, all right? So like if you had 3 and 7, the example that we took, if you're doing 3 times 7, that is 21. It is obviously not a prime because you just multiplied two numbers to get there. So how can it be a prime, right? So the question is, how many of these generated numbers will be prime? See, it's quite simple. Only those places where you have got exactly one of the numbers raised to the power 1 and all others as 0, only they will be prime. So 3 power 1, sorry, not this one, 3 power 1 times 7 power 0. This will be prime because, well, here 7 power 0 is 1 and 3 power 1 is 3. So that is a prime. And the other one will be this. 3 power 0 times 7 power 1, which is basically 7. These are going to be the only two numbers. So in general, how many numbers are we going to get? We're just going to get m numbers. One for each of the given unique primes. So the answer to this is simply m. All right. Let's see another problem application type, which is slightly more standard. Can 8 power n end in a 0 or a 5? Right. Now they can change 8 to 6, 4, 2, even 5. So you have to be careful. You should not mug up things. You should really understand. Let's see for the specific case of 8 power n. What is it that we deal with? Cool. So we have been asked to show that it cannot end in a 0 or it can't end in a 5, right? So let's take them case by case. First case, why the number can't end in a 0? Well, it cannot end in a 0 because let's say that there is some number that ends in a 0. Let's call it k. So maybe k is something like 210, or like randomly chosen number 210. If k is 210, we are saying that you can write that as p times 10, where p is some natural number. So here, in this case, p will be 21. We can write 210 as 21 times 10, right? you can always write a number that ends in a 0 as p times 10, where p is some natural number, right? So if this is indeed a power of 8, we should have that 8 power n is equal to p power 10, and that n is some natural number, right? N is equal to some natural number for which this happens. But we'll see that that cannot actually happen. All right, why? Because 8 power n is 8 is basically 2 cube, right? 8 is 2 cube. And if you raise 2 cube to the power of n, that's like saying you're raising 2 raised to the power 3n, right? And from the right hand side, you have got this 10 as 2 times 5. If we just club the 2 with p and the 5 outside, you will see that this is 2p raised to the power 1 times 5 raised to the power 1, right? Now you could have written this as 2 raised to the power 1 times p raised to the power 1 times 5 raised to the power 1. That really doesn't really make a lot of difference, right? The important thing is that you're getting a 5 outside here, right? And there is no 5 on the left hand side. So that means this is what we call as a contradiction. This thing can never be true, right? That's a contradiction. Because your left hand side does not have a 5, your right hand side does have a 5. Similar case for ending in a 5, all right? The solution is right here. If k is ending in a 5, you can write k as p times 10 plus 5. Now you should basically derive this as to, like, why does it make sense? Not derive per se, you should understand. If that is the case, you can write 8 power n as 10p plus 5. You take 5 common. You'll again end up with the same contradiction that, you know what, there is a 5 on the right hand side, but there is no 5 on the left hand side. So that cannot be the case. We'll come to the last topic for this video, which is LCM and HCF, right? LCM is lowest common multiple. So if you take two numbers, like let's say maybe 4 and 6, what is the smallest number that is a multiple of both of them? By trial and error, I believe you can get that number is 12. 12 is a multiple of both 4 and 6. And it is the smallest such number, right? Don't say 0. 0 is never, we don't consider 0. This result is true for natural numbers, all right? And HCF is basically the highest common factor. So let's say if we have 9 and 12, which is the largest number that divides both of them? For now, by trial and error, we are saying that that is 3. There is no number that is more than 3 and that simultaneously divides 9 and 12, right? Like 4 divides 12, but 4 doesn't divide 9. So the idea of LCM and HCF as such is not new. We have learned that in lower grades as well. We'll be using prime factorization to basically arrive at this. So we say that you write down the prime factorization of the two individual numbers, all right? And you'll see that the product of the smallest power of each common factor will give you the HCF. And the product of the greatest power will give you the LCM, right? Now, why is that? Well, we'll see. Let's take an example. So LCM and HCF of 20 and 24, we have to find out, right? So first thing we do, we write down the prime factorization of 20 and 24. Here I've written it down. 20 is 2 raised to the power 2 times 5 raised to the power 1. 24 is 2 raised to the power 3 times 3 raised to the power 1, right? So if we write it down a bit more properly, you know, in a bit more organized manner, we can write them like this, right? Cool. So nothing fancy up till here. All we have done is written the prime factorization. Now, you may wonder, where did this 3 power 0 come from? Well, you can always have 3 power 0, right? 3 power 0 is 1. You can always multiply a number with 1 and not change its value. A power 0 is 1, right? Here's the catch. Obviously, a cannot be 0 itself. So this is true for all natural numbers, all right? Now, let's read the statement again. It says product for HCF, product of the smallest power, right? Cool. So if you talk about HCF, both of them have got a 2. Which is the smaller power? 2 power 2 or 2 power 3? It is 2 power 2. So you will take 2 power 2 here. By similar reasoning, the powers of 3 are 0 and 1. Which is the smaller one? 0. So we get a 0. For 5, the smaller one is 0. So we get 2 power 2 times 3 power 0 plus times 5 power 0, which is just 4. For LCM, we have to take the highest power, right? For LCM, you have to consider the product of the greatest power of each prime factor, right? So between 2 power 2 and 2 power 3, 2 power 3 is bigger. Between 3 power 0 and 3 power 1, 1 is bigger, and similarly 5 power 1 is bigger. You'll get the overall answer as 120. All right, this is a direct application. There's nothing fancy about it. Cool. Then we notice a result which is also, you know, quite common. If the two original numbers were 20 into 20 and 24, if you multiply both of them, that you get a 480. And if you multiply the LCM with the HCF, you still get a 480, right? So that means LCM into HCF can be equal to the product of two numbers. Now, this is not a coincidence that always happens. That is true as a general result. It is as true as the fundamental theorem of arithmetic, all right? Now, you can kind of leave it at this, but you can also, go down one step further and try to understand why that really works, because there's really no mystery about it. It's pretty much basic common sense, all right? I'll tell you this. Take any two numbers A and B, all right? You can take them to be the same, take them to be different. For the argument's sake, I'll take them to be different, all right? So maybe A is, let's say 10, B is maybe 15, all right? I've chosen them randomly. Now, what is A plus B? A plus B will basically be equal to 10 plus 15, which is 25, right? That will always be equal to the minimum of A and B, which is, what is the minimum of A and B? With the minimum of A and 10 and 15 will be 10, right? Plus the maximum of 10 and 15, which will be 15. So you'll always get that 10 plus 15 will be equal to 10 plus 15, right? You might ask, all right, this does, seems to make sense, but isn't this redundant? Like, why would you even do that? Well, if you think about any particular prime number, all right, prime number in the factorization of two numbers, let's just take maybe the 2 in both of these, all right, here. When you're directly multiplying them, what you're doing is you're doing 2 power 2 times 2 power 3, right? Now, obviously, you're doing the other prime number multiplication as well. But if we just talk about the 2, what you're doing is you're doing 2 power 2 times 2 power 3, right? Now, law of exponent says that when you have the base common and the powers, then the overall result is that the base remains the same and the powers get added. So you're getting 2 raised to the power 2 plus 3. We'll just leave it at this. Cool. When you take the LCM, what do you do? For LCM, you take the greater power, right? Or the max. The max. So that means you're going to get 2 power 3. And when you take the HCF, you take the min, right? So you will always take one of the two, all right? And as long as you're multiplying LCM times HCF, you'll take both of the two. So therefore, once you multiply LCM and HCF, you are going to get